Hello, have you ever wondered how a plane able to fly? By the way, my name is Afifa Devin Amadou, MA1A100. So let me introduce you guys to the most magical principle in the world that able to fly a plane into the sky. The most magical principle is actually Bernoulli principle. Bernoulli principle is a huge name in the fluid mechanics world. So what is the uniqueness of the Bernoulli principle that makes it very famous? So actually Bernoulli principle discovered by a Swiss Dutch mathematician known as Daniel Bernoulli. According to Daniel Bernoulli, Bernoulli principle occurs when the velocity increases and resulting to the decrease of pressure. So he made an equation that consider pressure, density, velocity, gravitational. However, we must note that the Bernoulli principle is not applicable to the real life situation. It's only applicable to the ideal fluid. So, ideal fluid actually is a fluid when the viscosity is zero. So, next is a Venturi method. So what makes a venturimeter is a good measurement for Bernoulli principle. So this is a venturimeter diagram. They have a three section: converse, diverse, and through. Actually, at converse and diverse section, it has a larger surface area. So when the larger surface area is indicates of the increasing pressure. So according to the Daniel Bernoulli, when the pressure is increased, the velocity is decreased. However, it is different to the throat section, or we can see it as a smallest part in the ventrimeter. So according to the Daniel Bernoulli, when the area is decreased, pressure will decrease. And when the pressure is decreased, it means that velocity is increased. So without wasting our time, let's know our experimental objectives. First is we want to study the Bernoulli theorem for incompressible fluid by using Venturi meter. Next is we want to measure the total pressure head, static head, and dynamic head at various points throughout the venturi. And lastly, we want to compare the difference between experimental and theoretical.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hakim Ismail. Today I will talk about theory related to the experiment 1. First is the Bernoulli principle. Bernoulli's principle states that the increase in the speed of the fluid occurs simultaneously with the decrease in pressure or decrease in the fluid potential energy. Bernoulli principle can be derived from the principle of conservation of energy. It is stated in steady flow, the sum of all forms of energy in the fluid will be the same at all points of the streamline, while the energy remains constant and the increase in the speed of the fluid will be implied there is an increase in dynamic pressure, which is the kinetic energy. The most general form of the Bernoulli equation is shown below, which is P1 plus 1 over 2 rho v squared plus rho gh equal to constant. This equation is the sum of kinetic energy, potential energy, and gravitational energy at height. If the equation was multiplied through the volume, the density can be replaced by mass and the pressure replaced by force times distance. As the replacement, we can see that the different pressure does work, which can be used to change kinetic energy, the potential energy of the fluid in this equation. Bernoulli principle also states that in a non-viscous flow along the pipe of varying cross-section, then the increment in the speed of the fluid simultaneously with a drop in pressure or decrease in the fluid potential energy, and the pressure increase when the pipe open out and fluid stagnate. Thus, pressure will decrease when the velocity is increased. This is expressed with the following equation, which is a P over rho g plus V squared over 2g plus z equal to h, all constant. From the formula, P is the fluid static pressure at the cross section, rho is the density of the flowing fluid, g is the acceleration due to the gravity, v is the mean velocity of fluid at the cross section, z is elevation head of the center at the cross section with respect to the datum, and h is total stagnation head. The sum of pressure head h, velocity head hv, and the elevation elevation head z is known as the total head. The total head at any cross section is constant according to the Bernoulli theorem of fluid flow through the pipe. This represents the total head at the cross section. This formula. Next is we explain about the Venturi tube. Venturi tube is a practical application of Bernoulli principle, and the Venturi tube has a air inlet that narrow to the throat constricted point and outlet section that increase in diameter toward the rear. This you can see the diameter at the intersection is large and then it become narrower at the center, and then it will increase again in diameter at the outlet. Diameter or outlet is the same as in the inlet. The mass of air entering the tube must exactly equal to the mass of exiting tube. At the constriction, the speed must increase to allow the same amount of air to pass in the same amount of time as all the part of the tube. When the air is speed up, the pressure also decrease. The past constriction, the airflow slow and the pressure will increase. Next is the venturimeter. The venturimeter is a tool used to measure the flow through the pipeline. This apparatus consists of venturi tube, which is this tube, and the pressure gauge, which is the manometer. The venturi tube has a convergent portion, a throat and divergent portion as shown in the figure below. The convergent portion function is to increase the velocity of the fluid and lower its static pressure, which is converging cone, convergent portion. And the pressure difference between inlet and throat is thus developed, which pressure difference is correlated with the rate of discharge. The diverging cone serves to change the area of the stream back to the entrance area and convert velocity head into the pressure head. Okay, this is a D is the diameter of pipeline and throat. Pipeline. I'm so sorry, this is wrong. D is the diameter of throat, which is D. P1, P2 pressure inlet and throat. P1 is head here, P2 is here. HM is the manometric deflection, the distance between this that will be calculated. That's all from me. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Afif Fidobi Shamsul Azman. So today I want to present methodology for the experiment 1 is a Bernoulli theory. For the method and procedure for the experiment, the first is the pitot tube and multi-tube manometers when valves have been opened. The volume is regulated and the pump is switched on while the valve in control. By reading the static and pitot, the water level measurement can be obtained. For the last procedure is the hole is closed and the time is recorded using a stopwatch and a water level indicator. So this is a experiment setup apparatus for the Bernoulli theory experiment. At A, we can see that it is a Venturi, and at the point C is a multi-tube manometer for static head measurement. And for the point E, you can see that is a apparatus for pitot tube for total pressure measurement. I think that's all for me. Thank you.
Assalamualaikum and hi, my name is Daniel Tazrin Amir bin Muhammad MA18085 and I'm going to continue on chapter 4 on lab 1 Bernoulli theory. For the overview, we have two parts, which the first one is result and calculation, the second is graph and discussion. The first part is the result and calculation. We are given by our lecturer the data set, which include the static head and the total head. We also given the diameter of the pipe and the volume in which is 5 liter and the time taken is 22 seconds. And this is the formula we use for our calculation, and next to it is the sample calculation where we have the formula for the volume flow rate, the dynamic head, the measured velocity, the calculated velocity and the dynamic pressure. For the sample calculation we use the first data value, which is the from the static head. We use the H1. For the total head we use the H1 total. For the volume flow rate, we can have the value in form of liter per second or meter cubic per second. And the dynamic head, which the total head minus the static head, and the value from the dynamic head we get, we use to calculate the measure velocity, whereby the calculated velocity, we use other formula, which is the volume flow rate divided by the cross sectional area of the duct, which is this d value here. Sorry if you cannot see, the d value here is the given value, which is the internal diameter, but we change it from the millimeter per second to meter. And lastly, the dynamic pressure, and this is the tabulated data version where we get the diameter, internal diameter for each point, the dynamic head, the measured velocity, the calculated velocity, and lastly the dynamic pressure. Next part is the graph and discussion. So this is the graph for head versus Venturi meters point, where the total, all three of the head are included in here, where we got the dynamic head, the total head, and the static head. So based on the static head pattern, which is here, right here, the first three pattern decrease as proven by theory, where the pressure decrease as the cross sectional of the area decrease based on the data here. The diameter, internal diameter of the first 3 points are decreasing. And for the dynamic head, it is associated with the velocity, unlike the static head, where as the cross-sectional area decrease, the velocity of the moving fluid increase, thus giving the first 3 points here increase. And lastly, the total head. The total head is the sum up of the dynamic head plus the static head. Where if we compare to other data set, if we compare to other groups data set, the pattern would be overlapping or will be quite similar, because the data given by us is moderately similar to each other. So in theory, if we increase the volume flow rate, we can increase the total head. Next is the graph for velocity versus Venturi meters location, and we include the measured velocity with calculated velocity. As we can see that the value for the pattern for measured and calculated velocity is quite similar, because but the the measured velocity is slightly lower than calculated velocity because there is some head loss in the pipe due to the fluid viscosity near the surface pipe. So therefore the value of the measured velocity of the moving fluid is slightly lower than the calculated velocity. And lastly, the pressure against meter's position. So for the dynamic pressure, the graph for the dynamic pressure based on the pattern from 1 to 3, the cross-sectional area is decreasing, which will increase the velocity of the moving fluid, which also increase the dynamic pressure as well. Therefore, it is proven by this graph pattern that the dynamic pressure is correlating with the cross-sectional area. So that's all for me. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syami bin Muhammad Zubair, MA 18117, and I will present about the conclusion. The objective of this experiment was to discuss the behavior of ideal and real fluid, and on the basis of the test result, it can be concluded that the experiment was successful because there is difference in measured and theoretical values. This is because of the friction loss in the real fluid. Ideal fluid does not have friction loss. From the experiment, it can be concluded that with decrease in area of flow, there is an increase in velocity and decrease in the flow pressure of the fluid. That's all from us. Thank you.